Hello everyone, so this is our first attempt at doing an exam review via lecture video. I do want to point out that you have a quiz on this day. So the day after you see this video, I guess, you'll have a quiz. It's going to be on electronic configurations. And furthermore, don't forget about note cards. You should have received a note card check sheet that will tell you what flashcards to make for the unit. And be thoughtful about whether or not those flashcards are helpful, because we don't have to do them all the time. It's just a suggestion this time. All right, so we'll just dive right into it. So number one, it says, what are the characteristics of a neutron? So going through the answer choices, I see it has no charge and no mass. That doesn't make sense, because I know that a neutron has a charge of 0 and a mass of 1. So I'm going to look for that. Yeah, I think that's basically number 2. So I'm going to go with that on number 2. It has no charge and a mass of 1. All right, so number 2, it says the charge of a beryllium-9 nucleus is. So here's the thing, beryllium-9, that's a mass number. And they want to know the charge of the nucleus. So the 9 in the mass number is actually, that's a number that represents all the protons and all the neutrons in the atom. So it actually has nothing to do with the charge of the nucleus. If I want to know the charge of the nucleus, I'm going to have to look deeper and use my periodic table. The periodic table tells me that beryllium has 4 protons in its nucleus, and I'm basing that on the idea that it has an atomic number of 4. So if the atomic number is 4, that means that it has a nuclear charge of positive 4, and the answer is 4. A lot of people miss this question because they think that this 9 is somehow a nuclear charge, but remember, this 9 is actually a mass number. Okay, in the third question, I can see it's going to be a math question. This is what we call atomic mass, when they give you like a certain amount of substance and they tell you how much of it is a particular isotope, in this case boron-10, and then they tell you how much of it is a different isotope, in this case boron-11, and then they're going to ask you to do some math to show what its atomic mass could be. So one thing I want to point out before we start on this one is that there was a 100-gram sample in total, and it contains boron-10 and boron-11. The boron-10 is 19.78 grams of the 100, and the boron-11 is 80.22 grams of the 100. And also 80.22 plus 19.78, you guessed it, those two things add up to 100. You can think of these numbers as percents because they are part of a 100-gram sample. So now that I know their percents, I'm going to go ahead and start going through what I think the setup should be. So first, I'll start working on boron-10. Remember when you do these setups that you need to multiply the mass number by the percent abundance of that element in decimal form. So in decimal form, it looks like it's going to be 19.78%, but in decimal form, that's going to be 0.1978. So 0.1978. That's the abundance of boron-10. So I need to multiply that by the number 10 because that's the mass of that isotope. And you need to add that together with another product, and the other product is going to be the percent abundance of boron-11, which I'm going to write down 0.8022, which is the decimal form of 80.22%, and that needs to be multiplied by the mass for that isotope, which is 11. So really, I just need to find an answer choice that looks like this. I'll pause the video and let you choose the one that looks similar. From my looking at the question, it looks like number 1 is our best answer. It matches right up. Okay, so number 4 says which 2 atoms are isotopes of the same element. So they have to be isotopes, which means two different masses, but it's the same element, or it can be different numbers of neutrons with the same number of protons. So that's why I'm going to take out number 1, because they're different elements. So isotopes have to be the same element. So using that same logic, number 2 can come out and number 4 can come out. And then number 3 is left, and it's the right answer for a couple of reasons, but it definitely is the same element, which is required for 2 things to be isotopes. But the other thing is that they have different mass numbers. So this number on top is the mass number, and they're different, and that's what an isotope is. So isotope is different mass numbers, same number of protons. So I went ahead and filled that in for you in case you need it. All right, so number 5, it says, which conclusion is based on the gold foil experiment and the resulting model of the atom? This is a very key thing to understand, but Rutherford said that the atom is mostly empty space and that the nucleus is small, dense, and positive. So let's look for that. Number 1 seems to be okay. 2 doesn't make sense because the nucleus is not negative. 3 doesn't make sense because the atom has lots of empty space. And same thing for 4. So I think 1 is the best answer. So 6, an atom of oxygen is in an excited state. When an electron in this atom moves from the third shell to the second shell, energy is. Okay, so when you go from the third shell, which is higher, to the second shell of an atom, let's say you're an electron and you're making that trip, you will always release energy. That's just a law of physics, is when you go from higher energy level orbitals to lower energy level orbitals, you will release energy. So when you go from third to second, energy is going to be emitted by the electron, not the nucleus. Let's start on number 7. It says, compared to an atom of phosphorus 31 and an atom of sulfur 32, all these answer choices have different numbers of protons and neutrons and electrons, and you're comparing those things. So I'm going to put in some information about both of these isotopes, and then I'll come back. So I went ahead and wrote down the symbols and their mass numbers in the top left. That's where that information always goes in this particular notation example. I'm also going to look up their atomic numbers on the periodic table, and that'll give me their number of protons. So I went ahead and looked those up. Phosphorus has 15 protons, sulfur has 16 protons. So I could definitely answer this question if it only has to do with neutrons and protons. And I just need to do one more step though, because I need to figure out how many neutrons each of these guys has. This is protons, that's protons. And I can find the neutrons, but this is just a mass number right now. So I need to figure out how to find the number of neutrons. So the way you do that is you subtract the atomic number from the mass number. So I will fill that information in and I'll come back. Okay, so I went ahead and did it. 31 minus 15 is 16, so that's how many neutrons it has. 32 minus 16 is also 16. So that's how many neutrons sulfur 32 has. So what that means to me essentially is that any answer choice saying that they have different numbers of neutrons in any way is going to be wrong. Now compared to an atom of phosphorus 31, an atom of sulfur 32. So we're focusing on sulfur 32. Sulfur 32 has an extra proton, as 16, whereas phosphorus has 15. So I'm going to say that sulfur 32 has one more proton. Okay, number 8, the mass of an electron is approximately equal to 1/1836, the mass of. All right, so we know that an electron's mass is 1/1836 AMU, but these answers are all subatomic particles, positrons, protons, alpha particles, beta particles. So I need to figure out how to solve that. I would say that what you should be thinking of is that certain subatomic particles have a mass of 1. For instance, A proton has a mass of 1 AMU. So that, and an electron is 1 over 1836. Therefore, an electron is 1 over 1836 the mass of a proton. Okay, moving on. We have a nice short answer here. And I'll read it out to you, and then we'll work on the short answers together in the video. So a glass tube is filled with hydrogen gas at low pressure. An electric current is passed through the gas, causing it to emit light. The light is passed through a prism to separate the light into the bright colored lines of hydrogen's visible spectrum. Each colored line corresponds to a particular wavelength of light. One of hydrogen's spectral lines is red light with a wavelength of 656 nanometers. Tubes filled with other gases produce different bright line spectra that are characteristic of each kind of gas. These spectra have been observed and recorded. Explain, in terms of electron energy states and energy changes, how hydrogen's bright line spectrum is produced. All right, I always advise keeping these very short. So I would say, I'm going to write in my answer and then I'll talk about it. So my answer is that electrons absorb energy and move up a level. They release energy as light when they move down. Next question says, explain how the elements present on the surface of a star can be identified using bright line spectra. So pause the video, think of an answer, and I will have mine written in when you come back. So here's my answer. I'm going to keep it short again. If they just want to know how you can identify the elements on the surface of a star, then all you need to say is compare the spectrum to a known spectrum. So you take a spectrum of the star that you are studying, that's your spectrum, and you compare it to some spectra that you already know, and you're looking for matches. So all you have to say is this sentence. Okay, so we've been doing number 11 just sort of like as we go, but this question is directly asking about it. But the number of neutrons can be determined by, you're just going to need to subtract the atomic number from the mass number. So it's definitely choice 2. So yeah, subtract atomic number, which is the number of protons, from the mass number, which is protons and electrons. So 12, which statement concerning elements is true? The only one I see here that's definitely true is number 4. It says all atoms of a given element must have the same atomic number, so that's definitely true. What I would suggest for all of you on number 12 is if any of the other 3 seem like they could be true to you, please make a note of it and ask me in class to explain why one of these 3 couldn't be the case. So number 13, it says atoms of the same element that have different numbers of neutrons are classified as. We can go ahead and say right now that that's called an isotope, but this is the definition of isotope. An isotope is atoms of the same element that have different numbers of neutrons. So that's just definition question. And in number 14, they want to know which electron configuration could possibly represent an excited state for aluminum. So here's how you solve questions like this. You need your reference table and the periodic table in particular because you need to look up aluminum and figure out what its ground state is. So pause the video and look it up, and I'll have it written when you come back. Okay, so the aluminum ground state is 283, and that means it has 2 electrons in the first orbit, 8 in the second, and 3 in the third orbit. They want to know which could possibly be excited. It's definitely not 3, because that's the ground state. And I could knock out some others right now, but I think we'll do this a different way. I'm going to explain what excited means to me. So excited means that you have an electron in an orbit above where it needs to be. So for example, this first orbit holds 2 electrons, and the second orbit holds 8, and this orbit can hold up to 18. But if you were to take an electron from this orbit and put it up here, it would make the electron configuration change, and it would also make the atom excited. So if I just took one from the second orbit and put it in the third, then I would have only 7 electrons in the second orbit, because I'd be losing an electron as it moves to the third orbit. And that would mean I would have 4 electrons there. So this is definitely excited, but it's also one of several possibilities, and it's not necessarily going to be in the answer choices. But, oh, there it is. I just checked, and it is there. And that's definitely an excited state for aluminum. So step 1, check your periodic table. Step 2, use your imagination and move electrons up to orbits that they don't need to be. All right, so moving further, which statement correctly describes the charge of the nucleus and the charge of the electron cloud? So, okay, so the nucleus is most certainly positive and the electron cloud is most certainly negative. So that's choice 2 from what I can see. In 16, given the table below that shows students examples of proposed models of the atom, in model A, protons are in the nucleus, electrons are in specific shells. That sounds like Bohr to me. In B, protons are in the nucleus, electrons are in regions of most probable location. That sounds like the wave mechanical model or the modern model to me. In model C, we have protons dispersed throughout the atom. It's strange. And electrons are in specific shells. I don't really know what model that could even be. And then in model D, it says protons are dispersed throughout the atom and electrons are in regions of most probable location. Yeah. So I don't think either one of these two makes sense to me. So let's see, which model correctly describes the location of protons and electrons in the wave mechanical model? So looks like hard work paid off. Model B. All right, number 17, which notation represents an atom of sodium with an atomic number of 11 and a mass number of 24? So you get to practice your notation examples here. So there's sodium. You might need to use table S to look up sodium and find its symbol, because a lot of you guys would write S for sodium, and that's not correct. That's a different element. So Na is for sodium. Now they say that it has a mass number of 24, so that's going to go in the top left. That's where mass numbers go. And they have an atomic number of 11. They didn't really need to say that, by the way, guys, because if they say sodium, they automatically mean to look at Na on the periodic table, and they all have the same number of protons, which is 11. So they didn't need to tell you both pieces of information, and since they did, that's just being nice. So that's what we're looking for. I see it here on number 1. All right, number 18, it says hydrogen has 3 isotopes with mass numbers of 1, 2, and 3, and it has an average atomic mass of 1.00794 AMU. This information indicates that. All right, so do you see how this atomic mass is really very close in magnitude to this mass number? So we have a mass number of 1 for one isotope, and then we have an average atomic mass of basically 1. It's a little bit higher, but it's basically 1. This information indicates that there are more isotopes that have an atomic mass of 1 than 2 or 3. So since more of the isotopes are this guy, you're going to see that reflected in the average atomic mass. All right, number 19, it says, what's the mass number of an atom that has 6 protons, 6 electrons, and 8 neutrons? So the mass number is the number of protons plus the number of neutrons. So there's the definition for that. And this particular guy has how many protons? 6. And how many neutrons? 8. I just got that from the question. So his mass number has to be 14. All right. Number 20. An atom has an atomic number of 9, a mass number of 19. Okay. I'm going to write in the symbol that I think. I'm just going to put an X because I don't know what element it is, but its mass number is 19 and its atomic number is 9. That means it has 10 neutrons. And it says it has an electron configuration of 261, so that helps out as well. That, by the way, I'm glancing at my periodic table, and I can tell that that's not a ground state for any element, because this electron right here could fit in that orbital. So this is not a ground state, from what I can tell. So explain why the number of electrons in the second and third shell shows that this atom is in an excited state. So, as I wasn't seeing it at first, but I can see now that what I was just discussing is what the question was asking. They want to know, how does this show that it's not, that it's in an excited state? So I would say, quite basically, that electrons in the third shell could have fit in the second shell. So I just wrote that answer in. Looks like I'm all set. All right, so here are the answers in case you need to scroll through them for any reason. You can pause, rewind, check your answers if you need to. They do give, in some of the short answers, they're giving you more than one option for your answer. All right, so you should have all of this stuff recorded as Cornell notes and definitely study for the exam. It's coming up.